So today, it'd be good to. Well, that's just the graphing of.
The falling objects.
It's really just like we really talked about it at the end last week when it's just the position, typically X, and then the Y. You're moving over some type of time, so it's like position, and if the go to it. How we were talking about position, velocity, acceleration, so it's really just slope, just some normal things. Hey, great day. Yeah. Hey, great day, Miss Amy. Hey, how's it going? Good. Everything's great. It's a little cold in here still.
Coming from the cold last week, being in here.
Dang. That's wild. Maybe somebody gave it to you.
I don't know.
I know J-Man said she wasn't feeling good.
When I left here, I sat in the car in the heat so I can kind of warm up. It was so cold.
Yeah, and I turned the temperature up last week, and it still feels like it said 74 or something. It said that.
54.
Yeah, it does feel a lot colder than 75. It's definitely not feeling very tropical in here. But yeah, that last part, it's just getting a graph, the slope, y-intercept, position versus time, velocity versus time, position versus time, velocity versus time, just understanding how each one works. But I don't believe we really have too many problems that you're really forced to really look at this super in depth, so of course with slope, y rise over run, y over x, this is just connecting our velocity, because velocity is position over time, or change in position over the change in time. Acceleration is the change in velocity over the change in time. So it's just saying you can get these equations from here. Here's a position over time. So and then you'll know that the slope is going to be the change in position, the rise, over the run, the change in time. So you're able to get your velocity, which you can also understand this position of x. So 2,000 meters would be the initial x plus the change in average velocity times time, which is our kinematic equation. So it's just letting us know that these equations are also able to be used for our graphing purposes. So that's with that, the slope of x versus t. That's the same thing. That's what we just talked about. Check our velocity and acceleration.
When you look on putting the lab together?
Well, not further than buying the materials.
I thought you started putting it together yet.
I haven't. I actually haven't. I actually went out of town this weekend. I went to Charleston, South Carolina. Yeah, we did a history and archives trip. So we actually learned a lot about Black history. We did
It's a lot of Charles.
yeah, and Hilton Head as well. So we went to a Gullah Geechee museum.
Geechee people. Oh.
And then we went to Charleston and did a church tour, like Black church tour. Yeah, African Methodists, Episcopals, and
That's where it all started.
Methodists. Yeah. So we learned a lot about that, and yeah, it was real cool. Got to roam around the city and the market, like the slave market and the market. The African American Museum. Yeah, it was parts of it was very heavy.
A lot of that stuff.
Yeah. After the African American Museum, I was just kind of like frustrated. I was just kind of mad. Hey, J Mac.
Good morning.
Hey, great day. With the new hair.
I made it to my place.
Oh yeah. Cause you walk so fast.
Yeah, that's debatable.
You walk so fast. So this is saying like the change in velocity over the change in time, which we know is acceleration. So it's just giving us different points where we're able to see, oh, okay, my change in velocity is the same as my change in time. So yeah, you don't really have to worry too much about that. But we could go over a little bit of like what we looked at last class. Chapter 2 talked about displacement, kinematics, motion, changing position, the change in velocity, the change in time, or the change in acceleration, and also the change in time. So vectors, scalars, coordinate systems, talked a little bit about that, but we're going to talk about vectors here. Time, velocity, and speed. That's what we just talked about. Acceleration. So here's a lot about that. Average acceleration. So at first we had meters, position, meters over seconds for velocity, and then acceleration, meters over second squared. Motion equations for constant acceleration. So we had our kinematic equations. So we got to understand that. So here's that that plus. Yeah, here's where they use that plus. I don't know why they had the minus on that first one. Anyway, problem solving basics for one-dimensional kinematics. Talked about that a lot. Examine the situation, determine which physical principle is involved, make a list of what's given, what's unknown, find the equation, and then substitute, check the answer, is it reasonable. Falling objects, so we talked about the gravity, gravitational acceleration, 9.8 meters per second squared, and then the graphical analysis, it's just looking at those graphs over how the motion works with, you're just plotting basically. Because we understand that since velocity is the change in position over time, that's what the slope is. When you're given position in time, we know velocity from the slope, so it's the same. It's pretty simple, but it's not too much to go there. All right, so chapter 3. there's something here. So this is what's talking about not everything is in straight lines. People typically are in curved lines. So he said that the tennis ball player typically would go in a curved line rather than a straight line. So we're gonna look at certain ways that they're curved lines.
It all comes down to the kick. In soccer, athletes become heroes because of their ability to skillfully maneuver the ball. Great players make the sport.
Wow. That is not very cool.
Look artistic. Although the soccer player does it by years of practice and intuition, if we know the speed of the ball just after impact, we can use physics to calculate the maximum height, known as the apex, as well as the distance it will travel before landing, known as the range. Calculate the velocity of the ball. We must first examine its horizontal and vertical components. We can calculate the height of the ball by using and a time needed to reach that height. And then determine how far horizontally it has traveled with. The player who leverages cleverly disguised physics will be the one who gets the fans cheering and wins the game.
Cool, little intro. Get our brains prepared. By the end of this section, we'll observe that motion in 2 dimensions consists of horizontal and vertical components. Understanding the independence of horizontal and vertical vectors in 2-dimensional motion. So this is talking about a block in New York City where people have to walk, gotta go from McDonald's over to Nike, and how are we gonna get there? Well, we gotta go X and Y, So that's what this is talking about. And then it goes into Pythagorean theorem, where c equals a squared, c squared plus, or a squared plus b squared equals c squared, where c equals the square root of a squared plus b squared. So if you're walking 9 blocks and then you walk 5 blocks, what's my resultant? What's the straight line? What's the path that I need to walk to get there in the most efficient time? So this is what would be the most efficient direction. The most efficient path would be a straight line rather than going over up. So this is saying 9 blocks plus 5 blocks, that's gonna be 14 blocks, as opposed to going on a straight line path. I could walk 10.3 blocks. So straight is always going to be better, but for the application of this is a helicopter. You can't go across these buildings unless you're in a helicopter. So it's a good sense to break it down in components, because that's the way we're gonna think about it in real life. That's how we're gonna have to actually walk. We're gonna do X and then do Y. But we can understand, this is actually the most efficient path. And then there's our angle. So we'll get into that a little bit more. So that's just talking about that, the independence of perpendicular motion. So this is talking about a ball. If you want to throw a ball, and then over time, that ball is going to drop, right? Because if I throw a ball, gravity's constantly gonna keep on pulling it down, so it's gonna come on down. So, and then you can calculate, okay, so I have my force of gravity, the green, and then over time, I'm throwing it to the right, so that's that black arrow, but then over time the gravity's gonna keep on pulling on it, so that's that, which they call, or which they let you know it's a curved path. At the same instant, another, for example, let's compare the motions of two baseballs. One baseball is dropped from rest. At the same instant, another is thrown horizontally from the same height and follows a curved path. The stroboscope has captured the positions of the balls at fixed time intervals as they fall. I've never heard of a stroboscope. I saw that earlier and I was thinking, what is a stroboscope?
Like a telescope.
I don't know. I have no idea. I've never heard of that before. Strobo. Yeah, I don't know what. Oh, strobes. Also known as a strobe. Strobe. That makes sense. Like strobe lights. Okay. That makes sense. Like strobe lights. Okay, cool. So we're learning something new. I wonder if biologists use this as like some type of understanding, like the most efficient path, or like ways that medicine travels or something in the body. What's a stroboscope used for? Measure the rotation speed or revolution velocity, frequency of rotating, vibrating, or moving parts, components, and equipment. All right, cool. This result means that the horizontal velocity is constant, affected neither by vertical motion nor by gravity, which is vertical. Two-dimensional curved path of the horizontally thrown ball is composed of two independent one-dimensional motions, the horizontal and the vertical. The key to analyzing such motion, called projectile motion, is to break it into motions along perpendicular directions. So we'll be able to learn about this. We'll also see how to break down vectors in the next section, vector addition and subtraction, graphical methods, and vector addition and subtraction analytical methods. All right, so this is our support in physically understanding a little simulation, seeing what's going on here. I'm definitely gonna need to tell Miss Nakia, because in the wintertime, how's this gonna be in December? All right, so this is a ladybug. It's gonna show our velocity and acceleration vectors. So this will be like a regular linear motion where your velocity is changing, and then, you know, just linear is pretty much constant, and then I can change the way Hey, great day. Welcome, welcome.
You made it.
So if I move this ladybug, then we'll see. So right now we're talking about chapter 3. We're in vectors. Talking about vectors now. And we'll get into projectile motion. So we'll see that our velocity is changing as I move this. So as you'll see, once the ladybug is slowing down, then acceleration goes the opposite direction. So that's something pretty cool to learn about, how our velocity is still going that way, but our acceleration is changing until velocity slows down. We're decelerating. On a circular path, our acceleration is inward. That's that centripetal force. So a centripetal force is very similar to this, where our velocity is going at an angle a little bit outside of the circle, going straight, but our acceleration going in meteorology and atmospheric science research, we deal with this because this is a similar path to how air flows inward to a low pressure system. So I can understand how this works through the low pressure systems. And then here's how it looks as an ellipse. Anyone know what an ellipse is? An ellipse? Ever heard of that before?
Like the thing that happens every so often, the moon is covered with all black something.
So you mean like the phases of the moon?
Yeah.
And caused by ellipses? Exactly. So yes, not exactly, but per se, but you're on the right track. Yes, in our solar system, in the astrological bodies flow, when we look at the rhythm of the astrological bodies, we see that they are actually ellipses. So yes, you're on the right track. The phases of the moon happen because of the difference of where the sunlight is hitting the earth, and then how much of the moon is being shown as opposed to the earth. So in our, you don't really have to know this, but the ellipses. So that's the sun. Here's our Earth. So that'll be a sign for the sun and the moon. So for a full moon, the direct amount of light is not being hit by the Earth. For a new moon is the opposite. So full moons that way. The new moon is the opposite. The Earth's, the sun's light is being hit on the backside of the moon, and then we get the what a lot of people would say quarter. That would be the other way, because the light is being hit. Yeah, so a quarter, boom, boom. So that's where we get those, where we have our quarter moon, first quarter, third quarter, and then a waxing gibbous, and then gibbous. A little bit is shown like that. Gibbous, and then crescent. So yeah, that's how the phases of the moon work. So you got new moon, crescent, and then you got first. This would be first quarter. I'm kind of doing this real sloppy because you don't really have to know this right now, but just to kind of go with what your question or what your comment was about the moon phases. You know, this is really the real reason of why we get certain phases of the moon. Gibbous, and then waning crescent, and then waning waxing crescent. So this is the real reason. These markers. It's probably hard to see, huh?
Yeah.
Yeah. So basically, just the sun over here. When the moon is in this phase, it's a new moon. We don't see it. It's dark. Well, to us, it looks dark because the sunlight is actually hitting that side of it. You know. But then on our, here's Earth. Anyway, boom, 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 boom. You know, so that's how the moon is getting. So and then on here, the light's hitting this side of the moon. So and then to us, this side is gonna look dark, and then third quarter, the light's hitting over here. So and then you'll see that side of the moon looking lit. So this is gonna be from here. You have. Third quarter, and this is first quarter. So from the new moon, you got the waxing crescent. Waxing, the way you remember waxing and waning. Waxing is when you like burn a candle, the wax builds. So that's one way you can think of waxing. Waxing crescent, waxing gibbous, first quarter. Gibbous, I don't really know how to think of gibbous for real, but a waxing gibbous is going to be building more light going toward the full moon. So you'll have a full moon here, and then you got the waning gibbous because you're losing more light because now it's getting harder to see. It's getting closer to the new moon. But then you got third quarter and then waning crescent. So that's how that works. But yes, you're right, because we say that there are no planets that go around the sun, pretty big, that all motions are gonna be elliptical. So there's certain parts where our Earth doesn't have like exact circles. You know, they say it's not exactly circular, that it's always gonna have a little bit of an ellipse. So an ellipse is a flattened circle. That's what that's saying. So you know, so and then we'll see some of the faster. So here's circular, so you can see the way that they draw it. A circle, and I want yeah, so here's circular. So you can see those faint lines. You know, we got circular going in a circle. But then ellipse, you'll see in the faint line. So you'll also see that the velocity changes a little bit too. So what's the velocity doing? Like when is the velocity getting stronger or getting